Hello, in this video we are talking about Newton's second law for rotation. We talked about torque, and we talked about it as a thing that can cause rotational acceleration. How does it do it? Well, it's basically F equals ma is what it is, just with rotational stuff. So let's get into it. Okay, so we know so far that we have a sort of rotational version of acceleration that we call angular acceleration. We have a rotational version of force that we call torque. And the question is probably, what's the rotational equivalent of m? Is it just m? Well, not quite. Um, m, if you want to think about m this way, it's a good way, and in terms of an inertia thing to think of it, when we say net force equals ma, I can think of m, if you want, as a ratio of F over A. It's kind of um, a measure of how much an object is going to resist accelerating when a net force is applied to it. In a similar sense, then, we can talk about how much will a thing resist rotating if a torque is applied to it. And that depends on what we call the moment of inertia. So moment of inertia is the thing we're going to talk about here. We're going to use capital I for inertia, moment of inertia. And like an object will have a moment of inertia. So like a door has a moment of inertia. A rod that's like being pushed or pulled to spin around, it has a moment of inertia. What it comes down to, and we're going to investigate this plenty as we kind of go, but what it comes down to is it depends on how the mass is distributed around the axis of rotation. So, like, where is the mass of the thing is the question. Okay, a higher moment of inertia is going to mean it's harder to spin or change its angular speed, just like a high mass means that the thing is hard to accelerate. So here's two examples to sort of show. Here's like two different things that have the same mass. So in the picture here, we've got a little kind of like wheel shape, like a little cylinder in the middle here. There's like green guy. That's like, pretty compact and all together and connected to like this big wheel. So this thing would be pretty easy to spin. But if I took this mass, this little green cylinder of like, some kind of dense material, and I instead took that same amount of mass but made it all around the edge of the wheel, it turns out, and see if this kind of makes physical sense, like picturing this, if you put all that mass around the outside, it is harder to spin it. So same amount of mass in both of these pictures, but if the mass is like on the outside, it's harder to spin than if the mass is close to the center where the spinning, the point that we're spinning around, the axis of rotation. Okay, so that's the basic idea, but there is, of course, an equation for it. And here's how we do it. The data booklet gives you, it gives you a total, but it's based on this. So this is for a point mass, just a single mass moving around some point, some pivot point that it's like rotating around. It's mr squared. So it depends on the distance between the pivot and the mass squared, and it also depends on how much mass. So when we're talking about a like body, an actual object, which we call an extended body or a rigid body, and that's stuff like a door or a rod or a baseball that's spinning or something. We can treat that as a system of point masses. So we're not going to literally do this, okay, so don't worry. But the idea is sort of, if I have a door, if I have a hinge here, and then I have a door, well, what I could do is I could take every single little atom piece of the door and I could be like, there's a mass right here. And the moment of inertia, that one little piece of mass is, here's like the R, it would be m times that R squared. And then there's another one here, and I could find the moment of inertia of that guy with the mass here times this distance squared. And there's another piece here, and I could do, mr squared. And I could add them all up and see what I get. Okay, you won't do this with a door and doing a adding infinity things. That's why a field of math called calculus exists to do that for us. You, of course, don't have to do calculus on IB physics, so any calculus the IB will do for you and just give you the answer. So realistically, you're going to do this with like two masses or something moving around an object, or like a mass on an end of a massless string, fun stuff like that. So anyway, what the data booklet is telling you is to get the moment of inertia of an extended body, the moment of inertia of a thing or a system of multiple masses. You do mr squared for each m in your system. You add them up. Remember, this is the sigma, which does mean sum, right? Just like in a net force. That means add up all the mr squareds if you have multiple m's. We'll do an example at the end of this video here to kind of show you what that means. It just means you do it multiple times and add them up to get the total moment of inertia if you have point masses. If you don't have point masses, you will be given a moment of inertia that comes from doing this adding of infinity little really tiny point masses in an object. And it'll look like this. All right, so, here's all these different things. We have like spheres have certain moments of inertia. Like a rod has a moment of inertia, and it's different depending on if you're spinning it around its center versus if you're spinning it around the end. A disc versus like a hollow disc or a wheel or something. Like these are slightly different. A teapot, if you spin a teapot around like this, it would have a moment of inertia that you can figure out by adding a bunch of stuff up. All right, so if you have something like a basketball spinning around, they'll tell you the moment of inertia of a basketball. And so you'll use that for I. There are always equations that look like this. It's like some fraction times mr squared. Or in the case of like a rod or something, they'll give you L for the length of the rod. All right, so you'll be given the equation unless you're dealing with point masses. And if you're dealing with point masses, mr squared for each point mass, and you add them up to get the total moment of inertia. Okay, so why do we care about that? Well, we said it's like the mass equivalent of rotation. And because we care about the relationship between torque and acceleration, and I said it's basically F equals ma, there it is. Just like in your data booklet where it says F equals ma, which is terrible because, well, they want you to just know this, which you should, but F means net force equals ma. Same deal here. Torque equals I alpha. Okay, so the Greek letter tau here is the net torque, the total torque, the sum of all of the individual torques acting on a thing, on an object, on a body. It turns out is equal to the moment of inertia of the thing times its angular acceleration. So it truly is F equals ma for rotation. And we're going to use it that way. Okay, so here's a little example of that same idea of angular acceleration and moment of inertia. So this is a little device that's pretty fun. It's the same mass both ways, and what it is, if you can see, there's like these kind of weights. These little discs are like screwed on to these long rods. And in the left side example, they're very close to the center. So your mass is all distributed pretty close to the center. Whereas here, you have those masses way out on the end of these legs. And so the mass is distributed way towards the outside, so far away from the center. So I would do like mr squared, mr squared, mr squared, mr squared. Add those up to get the moment of inertia. Same deal here, but r is way bigger, so it's got a way higher moment of inertia. And if you can see, they're just using a hanging mass for the force causing torque. And same hanging mass, same distance from the rotation point. So I should have the same total torque in both cases. But because this one, the mass is way super spread out, that same torque will cause a much smaller acceleration here in rotational sense than it does here. This one starts to rotate real easy, and it's rotating faster and faster and faster, whereas this one takes a lot longer to get going because more I, smaller alpha. Yeah, same thing. Is F equals ma. This is just like you're pushing two boxes. This is a little box. That's a big box. You're pushing them with the same force. The little box accelerates faster. Okay, this one, just the box. The M of the box is a little weirder. Got to do with how the mass is distributed. So let's try an example together. Such a fun one where I have 2 point masses connected by a rod. So this is like the example where you're going to deal with point mass stuff. This is what they'll look like, and this is as bad as they'll get. They'll give you like 2 point masses or something like this. So these 2 points are going to rotate around the center. So we're assuming they're like fixed in place at the middle here. And there's a 25 Newton force applied at a certain angle to one of the masses. The force acts for 2 seconds. I want to find the final angular speed of the system. Oh boy. Oh, this one's so fun. All right, so I want to kind of think from backwards. I'm trying to find final angular speed. That's already a clue to me of what I'm going to have to do eventually, because we're talking about, remember, angular speed, we're talking about omega. So I want to find the final omega, the angular speed at the end. Um, okay, so what it is, I think I'm going to have to use the rotational Suvat equations because I'm given a t, and so far the only equations we know that deal with any of this angular speed stuff are those kinematics equations for rotation. So I know t is 2 seconds. I got like an F and an L and a theta, which those don't necessarily apply to this. But let's think what else I got. Let's I might start by making a little basically Suvat table, but it's not Suvat. So the S equivalent is, remember, delta theta, angular displacement, initial velocity, final velocity, acceleration, and time. So, okay, I'm doing this because I know this is what I'm solving for. And so an equation that uses 4 of these variables is what I want. Okay. The dash because negatives. What else do I know? There's one other thing I know. I don't know quite enough yet, but I do know one other thing. So see if you can think about it. What's the one other thing we know besides time, which we're given? I think we know, or at least should assume here, maybe it's not spelled out super clearly in the problem, that this whole system looks to me like it starts from rest. So what we're going to do is we're going to put in for initial speed, let's put in 0. And I'm going to put radians per second just to remind ourselves that that's how we'll do angular speed stuff. So I'm assuming it starts from rest, and I want to find final angular speed. Well, remember how these work. You got to know 3 things to solve for a 4th thing. So do I know the total angular displacement, like how far in radians this thing will go around and around and around? Well, I don't think so. So, I think that means I'm going to have to try to find this angular acceleration. Can I do it? You betcha. You know what I'm going to do? Just like when we had Suvat problems where then you went, oh, well, I can use F equals ma to find the A, and then I can Suvat. Same deal here. The equation we're going to use to get our angular acceleration is this net torque equals I alpha equation. Because I can find the total torque. I've got a force at some distance with an angle. So I'm thinking about the torque equation. I can find moment of inertia with this add up a bunch of point mass nonsense. And so if I can use this equation to find the angular acceleration, I can then plug that in over here and find the thing I really want. Yeah, so this is very much a dynamics problem, a rotational dynamics problem, where I'm combining F equals ma and Suvat. Now I'm combining torque equals I alpha and the rotational kinematics. It's the same process, even if you don't feel like it is, because these letters are different. All right, but it is the same process. So let's go through it. I want to find like net torque. Let's do that first. All right, so what's the torque? Well, I'm going to go. Luckily, I just have this one force happening. So I think it's being caused by this here force. So the torque acting on this system is going to be RF sine of theta. All right, so let's see what we're dealing with. My R value would be from the point of rotation. So from here to where the force acts here is the question. The length of the rod is 3 meters. So I'm thinking the value for R I'm dealing with, I'm going to take half of that because this is half of the rod. So 1.5 meters is my R. I'm given F, which is 25 newtons. And that theta, that 30 degrees is the theta in the equation. I always want to kind of make sure, but it is the angle between R and F. So 30 will work here. Okay, so let's plug in and find the torque that's acting. So I'm going to do 1.5 meters times 1.5 meters times 25 newtons times the sine of 30 is what I want to do. 1.5 meters. We'll put that in our calculator. I know the sine of 30 is a half, right? Unit circle, unit circle. Okay, so let's calculate this real quick. We're going to do 12 and a half times 1.5. I'm thinking we get 18.75 Newton meters of torque. All right, there we go. That's this. Again, let's think about what I'm doing. I'm trying to find this so that I can put it in here so that I can ultimately find my unknown of angular speed at the end. So I need one more thing. I need I. So let's do this as our other step. To find I, I'm going to use the equation for moment of inertia, which is add up all the mr squareds. All right, so this is what it looks like when you have multiple point masses. Essentially, this big blue mass and this little red mass both have a moment of inertia, depending on their mass, and r, how far they are from the point that they're rotating around. And I'm just going to add them up. Right. So let's do red first. So the first one, the red one, is going to be 2 kilograms is the mass times r squared. Again, r is 1.5 meters because this mass is also, halfway. So its distance from the center is 1.5 meters. That's what r is. So distance from the point we're rotating around, let's say the axis of rotation officially. And we're going to add that to the other mass's moment of inertia, which will be here 5 kilograms, also times 1.5 meters squared. Okay, so let's again put that in our calculator. So I get 4.5 plus 1.5 squared times 5 is 11.25. And add them up. I get 15.75 kilogram meter squared. That's my moment of inertia. Hey, we're getting close now. All right, again, the point of doing this was to find my angular acceleration. So let's do that with, now I'm just solving for this, which is, so it's going to be net torque over moment of inertia. So I'm doing, let's see, 18.75 Newton meters over 15.75 kilogram meters squared. Okay, 18.75 divided by 15.75 gives me a fun answer. Yellow is great. Of 1.19 blah blah blah. 04 something something something. I'll do 1.1. The units are going to seem a little weird because a radian is a weird kind of cheater unit. But I'm going to get radians per second squared here because I know I'm finding angular acceleration. So that's what I'm going to put in for alpha for 1.19. And now I just need to find the equation that will get me what I want. So this is 1.19. All right, so now I go to my data booklet and I go, okay, I did all that. Now I'm going back to the beginning. I'm trying to find final angular speed based on these 3 other things. The one I always focus on for kinematic stuff is what do I not know? Well, I don't know angular displacement, so I want to pick the equation that doesn't have that in there, which is going to be like the v equals u plus at version. So final equals initial speed plus angular acceleration times t. So my final angular speed is going to be my initial, which was just 0, plus this 1.19 radians per second squared times the amount of time that acts for, which is 2 seconds. So I double that and I get 2.38. Let's round to 2 sig figs. And I get 2.4 radians per second. All right. Very fun problem with multiple ideas in there. I got rotational kinematics. I got Newton's second law for rotation, the kind of equation for torque. That's really everything we've done so far in terms of rotation. There it is. Again, hopefully the theme is, as dealing with different variables and some of these concepts like torque is a little different. It is very much the same process as regular mechanics that we're used to. And so as we practice, try and make those analogies in your head of how is this similar to what I've done before. This will help reinforce the mechanics stuff as well as get you better at the rotation stuff. All right, so have fun.